I really appreciate you joining in class. I really think that brings the spirit, and I'm grateful that you all will be willing to do that. So, in fact, teaching at BYU is awesome. I really love teaching at BYU for various reasons. But one is that we get to bring the spirit into our class, and for those of you that have had me before, you know that there's a very specific way that I like to do that. So for those of you who don't know me, I've often thought hard, how do we bring the spirit and sort of gospel insights and things like that into a highly technical class about deep learning and computation graphs and loss functions and things like that. And I decided sort of when I was early on in my BYU career that I didn't want to force it. I didn't want to do something unnatural or make it feel like something that wasn't genuine. And I thought, well, what can I say to you that's genuine and potentially useful to you? And I thought, well, I guess I just want to talk to you about my life. So every now and then, usually on Mondays, I will share just a brief devotional thought, usually harvested from my family. And so today, I wanted to start off with a devotional. Some of you may have seen this picture before. I try to keep it fresh. This is one of my kids, two of my kids, sorry. So my wife has this wonderful tradition in her family. Every semester before school, her father would give her and all of her siblings a blessing before school, father's blessing before school, just for the semester. It's not a tradition that I had growing up. So when I married her and got to know the family and saw this, I was like, this is really neat. I'm going to do this in my family. So we've been married 16 years. We have 9 kids. And so we do this at the beginning of every semester. Father's blessing. This is a marathon. I mean, there's a lot of blessings that are being given. And it's kind of tiring, but everybody's sitting there, and they're watching these blessings. And so a year or two ago, when we did this, at the time, this is my youngest, Caleb. So after we had done all the blessings, Paige, my daughter, was still sitting there in the chair, and Caleb runs up to her and puts his hands on his head, and he starts mumbling something. And he was giving her a blessing. And I thought, oh, this is neat. And I thought, I am grateful for the gospel. What we're seeing here is we're seeing the patterns of the gospel rippling through the generations. My wife's father did this for her. We're doing it for our kids. Our kids are seeing the pattern, and they want to do it. They're feeling it. And it's invariably a really neat spiritual experience. And I just wanted to share that with you. I thought, I hope that all of you are also trying to live the patterns of the gospel. I think you'll see as you have families and kids have grown, you'll start to see those patterns ripple through the generations. And it's a very powerful thing to realize that the gospel is in good hands with our kids, but also powerful to realize that even when they're this little, they feel it, they see your example, and they want to do what you're doing and be the kind of person that you are. So just hope you'll think about that and just take to heart the words of the prophets when they ask you to read and do family home evening, all of those things. They really do build a solid foundation for your families. So I hope that's a helpful thought for you on this beautiful Monday morning. In the name of Jesus Christ, amen. Amen. You're going to hear a lot about my kids this semester. So get to know them. This is Caleb, and this is Paige. So we'll talk more about other kids later. Okay. Business. Okay, so probably hit like that more. Okay, so let's talk about labs and readings. So lab number 2, the spec is up. So it's get to know PyTorch. This is going to be an unusual lab for most of you. So we are throwing you into the deep end of the pool with something called PyTorch, which is a deep learning framework. And what we're asking you to do is watch a video, which our TA Robert has put together. Incidentally, he told me that there's this section kind of in the middle that lasts about 8 minutes. And he's like, he couldn't get something to work. He's like, okay, I'll edit this out later. But it didn't get edited out. So you can fast forward past that part. So we want you to watch this video. What Robert does is he narrates about a page of code. So what you'll find in this class, the programming in this class is very interesting. Most programs that you'll write are only 2 or 3 pages long. There are not a lot of lines of code, but you'll find that each line is super important and does crazy amounts of work. So what Robert's done is he's given you about a page and a half of code, and essentially all you have to do is watch this video and type it in. But he's explaining each line and what it does. You're not going to understand most of this at this point, and that's okay. The point of this class is to just get you comfortable a little bit with PyTorch. The stuff we're giving you is boilerplate code that you'll probably use again and again and again over the course of the semester. So we just want you to have it right now. Also, but there's a couple modifications. So once you've sort of typed in the code and sort of understood, hopefully, how it works, The modifications are, I want you to take the base code and then do two things, and they're outlined in the spec. You need to implement what's called a validation loop or testing loop, and then do a little plot, a little visualization using Matplotlib. And examples of all of those are on the left, are on the spec. So, and we want you to Google, okay? So like, once you get comfortable Googling around for PyTorch examples, PyTorch documentation, PyTorch tutorials, like that's all fair game for this lab. We just want you to get comfortable with it, okay? If you have questions, so we really, really, really don't want you to get frustrated with this lab. If you like get hung up at all, start asking questions. Robert, you want to raise your hand? This is Robert, our like commando TA. So Robert has extra like time and availability this week.
For this lab.
Take advantage of it. So if you need help, please, please, please ask. He's going to be on Piazza a lot, trying to have a low response time. So just don't get frustrated. You'll get frustrated with later labs for different reasons, but not on this lab, okay? Okay, any other questions about this? Also, sorry, good questions. Okay, readings have been updated, so please check so the readings for about the next 3 weeks are pretty much solidified. I think I need to add one reading for this week, which is PyTorch tutorial. But then the readings for the next couple weeks have been divided into required and optional. Let me know how that goes for you. I don't want to take a whole lot of time, but I do want you to be reading these things. And then don't get too far ahead though, because for about 3 or 4 weeks into the schedule, it's still a little, we're not quite sure how it's going to shake up. So there's still, things are going to move around a little bit. Okay? All right, any other questions? Question, yeah?
Logistically speaking, is it the best place to ask questions on Piazza or what? Or in class, or what would you recommend?
So if you have a question that could be asked on Piazza, that's better. We can take class time. But if it's a burning question, obviously, I want you to ask it here. So it's up to you.
Okay.
So like if it's a logistics question that would be of general interest and it's a quick answer, like yeah, you can ask it here. If it's some crazy detailed technical question that's not of general interest, ask it offline. Okay?
I like when the general interest ones are on.
I'm sorry, what?
Oh, I like when the general interest ones are on Piazza, because then if I forgot,
Yeah.
I can look it up later.
Okay, well, you can ask it both places. Okay, question in the back. Yeah, go ahead.
I just had a quick question about Piazza. I know
Yeah.
last week you had mentioned that you were open to the idea of looking at Slack instead.
Oh,
And now that we've all had kind of had a week to work with it, just kind of interested to see the temperature of the room. And feel free to shut this down if it's way too early in the semester to talk about that. I personally wasn't all that impressed with Piazza. I would prefer Slack, but I don't know how others.
David.
So,
So the TAs can join the BYU CS Slack, and then we can have a channel for people to ask questions there for like real time. But I think the types of questions that you might ask on Stack Overflow should still be on Piazza, because if other people would benefit from the answer, then it should be on Piazza.
yeah, so the issue that we've had in previous semesters, I think maybe I explained this, was that we would set up a Slack channel for the class and we'd have different sub-channels for each lab. And we found that there was great chatter, but when people would come to those looking for answers to specific questions, like they'd scroll back through hundreds of messages. Whereas on Piazza, we can break it out and like pin things, and I've heard that that's useful. We do lack the real-time like notifications and things that Slack has. I would say let's give it a little bit more time, maybe a week, just to see. But I'm also happy to, we can do both if you want. I can start a Slack channel.
I prefer to have it one-on-one.
Okay, we'll vote strongly against both. Let's give it another week, but please raise it again if you're feeling, now this is a great experiment. I've never used it before, so I want to do whatever's best for you guys.
Yeah. I'll probably not raise it again. I'll let someone else.
Okay.
Make it second promotion in the week.
Okay, great, go ahead.
What takes precedence in the readings, the section number or the pages that are listed? Because I'm using a PDF version and the pages don't line
Oh,
up.
it might be, that might be like a version difference.
Section? Yeah.
Section number, obviously.
Okay, gotcha.
Good, any other questions? Okay, then let's dive in. So today, last time we talked about linear algebra, and we talked about dot product, and we talked about specific intuition about dot products, which is what? The dot product represents the similarity. Good. And we talked about how you should interpret dot products as similarity, matrix vector multiplies as similarity, matrix multiplies as similarity, etc. and we talked about cats as our running example. So today we're going to talk a little bit about, we're going to go beyond loss functions and talk about score functions. If we have time, we'll get to computation graphs, multi-layer nets, and we'll start talking a little bit about optimization. Okay, so loss functions. How many of you have heard the term loss function before? Oh wow, in what context? Where? They're reading. I don't know. Like, okay. Karma plus plus, grade plus plus. Well done. Okay. So yeah, so have you heard about loss functions other places? I'm just curious if this is a common terminology elsewhere. Go ahead.
In a stats class.
Stats class? Okay. Yeah, so lots of optimization sorts of things have some sort of function that you're trying to optimize. Sometimes it's called a cost function, sometimes it's a utility function, sometimes it's a loss function, sometimes it's a regret function. We're going to call them loss functions. That's the terminology in use in deep learning. So here's where we were. So far we've defined this, in our case, linear score function. So remember the example was we have a bunch of classes, we have a bunch of inputs, we do this linear image times matrix multiply, and we get a bunch of scores out. And we're interpreting these scores as numbers right now, but we'll talk about other ways to interpret them in just a second. They'll always be numbers. What I mean is we'll give them specific meanings in just a little bit. But right now we're saying that numbers, so numbers in bold are the true class, and we want those numbers to be high, and we want every other number to be low. Okay. But right now we have a lot of numbers. So we have 3 images, 10 classes, and we have 30 numbers. If we want to optimize something, really we need just one number. And so a loss function is something that takes something, for example, like a bunch of scores, and converts it into a single number that will describe how happy or unhappy we are with all of those scores. Then we'll do things like optimization algorithms, which we'll describe in subsequent lectures, that will find the parameters. So what were our parameters in our little linear model? What was it? It was, I hear you mumbling at people. X. Okay, what was X?
It was the input picture.
Now X was the input image. It's W. W was the weights. So remember, we multiply the image by the weights, we get a bunch of scores out, and
Wait, so was W just random pixels basically, like, or randomly assigned array?
okay, sorry. So we said a couple things about W. At one point we said what happens if W is random, and we got like for random numbers. That was these numbers. Another point we talked about, well, what if we had learned optimal W's, and that's when we got eigencats.
So like the fact that automobile is like is correct in this case is just random. Basically?
Yes,
So
that was sheer luck.
Okay. I got it.
Okay, good.
Wasn't this the average ones? The eigen stuff?
I don't think so. I think these were random.
Or these are random?
Well, it doesn't matter. I'm pretty sure these were random. Okay, so, and then eventually what we're going to do is we're going to find algorithms that will help us adjust those weights, the W entries in that W matrix, to improve these scores, and that will be reflected by an improvement in our loss function. So we're going to go through a couple of examples of loss functions. We're going to use this little simplified example. We have 3 classes, 3 images, and we have little numbers for each. So this is a cat, so that one's correct or not correct?
Not
Not correct. This one's supposed to be an automobile.
That one's correct.
Correct. And this one's a frog.
Not
Not correct. Okay, good. So we'll start off with something called the multi-class SVM loss. So how many of you have heard of a hinge loss or support vector machine loss function? Okay, just a couple of you. So this is one example of a loss function that helps, remember, the intuition is it helps us describe if we're happy or we're unhappy with these. So are we unhappy or happy with these numbers?
We're
Unhappy. We're unhappy because we want this to be a cat, we want this to be an automobile, we want this to be a frog. Okay, so a big part of this class is we're going to try to learn how to intuitively understand mathematical snippets, the little mathematical equations. So let's see if we can work our way through this one. So I would like you all to take a look at this function. Here's the description. And I'd like you to get with your neighbors and discuss this function and see if you can explain it to me in English. So this is like an equation that you'll probably find in some paper somewhere. Okay, so I want you to talk to your neighbors. So let's go through, but let's make sure we all understand what the notation is. So given an example, xi, yi, where xi is the image. So what's the dimension of xi? 3072, right? Okay? 3072 by 1. And yi is the label. So what size or shape is yi? It's just a scalar, one number, and it represents the correct class. Okay, we're using shorthand for the scores, so S is some function of xi and w, so how big is w? In this case, how big is w?
3,000, whatever, times
The number of
10.
pixels.
Okay, so 3072
Times 10.
columns by,
By 3, I guess, in this one.
yeah, by three, probably 3 rows, because we have 3 different classes here. Right, go ahead.
Could you describe why yi isn't a vector of all of the outputs?
Oh, yeah, so, good question. Why isn't yi a vector of all the outputs? And the answer is because it's subscripted by I.
Oh,
Okay, so it's saying this is the ith, this is the label of the ith example in your training set. And x is the ith input image.
That's not the output label, that's the.
I'm sorry, the output label.
That's
Yeah,
the
output label. Correct output, the correct label, the training label. Okay, so talk to your neighbor, talk to your friend, see if you can figure this out. Describe this equation to me in English. Okay? So we'll take 1.5 minutes. Go. 90 seconds.
So the loss for why I is correct or is that the way that we yeah, so what where everything is not.
So S is a vector of scores. yi is an integer. So S, like if they were talking about the fifth example, so what's the label for the fifth example? And then S, whatever that is.
So negative if we are
0, 1, or 2.
undershooting or overshooting.
So if you predict it correctly,
So I don't know why we're doing that.
but and then from 0 to yeah, that's negative.
Depends on which
Well, if it's correct by a value of these scores, these to 1. And so because they want to be like, have confidence that it's 1 away by the score. Otherwise, they're like, so is it, just to make sure,
All right, let's talk about it. Okay. Okay, so there's actually, all you noodle this and you're like, oh, there's actually quite a bit going on in this one little line of math. So who's got some thoughts? Give me some. Go ahead. Marissa.
So, for all of the wrong labels,
Okay, wait, whoa. Okay, slow
so
down.
j hat equals yi, we're going to sum over all of the other labels that are wrong.
Okay, so.
Because we know the
so-
true one. That's
right,
why
so this is a sum. Right, so we're summing over all things.
yeah, all
And
of the, yeah.
J ranges over everything, but it's not whatever the true label is of the ith instance. So just to be concrete, we've got the 42nd instance, and its label is like dog, or that's not an option, car. So we're going to sum over cat and frog. Okay, good.
So then SYI is the score for the true value. And if we got it
So
right,
whoa.
S sub
SYI.
YI, yeah.
Okay, so let's say
that's the bolded one.
So those are the bolded ones, right? So this is, notice this is S sub Y sub I. So the way you read this is, okay, take the ith label, which is, say,
it's the correct label.
cat, correct
Yeah, the
label,
label, yeah.
and it's going to be the score of the cat, okay? Or
Yeah.
so we're going to, but it's the, okay? And that, so does this depend on J?
No.
No, so as we're summing over all of these, this term is constant, okay? So this will always be the score of the correct thing. Good, keep going.
And then if we did it right, the score for the true value should be the highest, which means it should be bigger than all of the SJs, which means that SJ minus SYI will be negative.
Okay, good.
So then the +1, we're kind of assuming it's like a kind of tolerance thing, because maybe your true score. Well, okay, so ignoring the +1 for a minute.
Yeah, let's ignore the
if those
+1.
are negative, so if we did it right, then all of those should be negative. And then since we're taking the max with 0, then we'll have 0 loss.
Okay, good.
Then if we did it wrong, then there will be some scores that are bigger than the true value, and so those will turn up positive.
Because SJ will be bigger.
Yeah. And then we were still thinking about what the +1 was doing, but I'm assuming it's some kind of like tolerance
Okay,
thing.
so first of all,
Yeah.
fantastic. That was great. Good job. Okay, well done. Good job. So yeah, so there's a lot going on in this little equation. So does anybody have any thoughts about the +1? Go ahead. Wait, let's go to the back row. Someone. Go ahead. Blue shirt. Yes.
So
Okay,
I
I'll
understand the +1 is just kind of like a desired separation from the correct values. So you could have a 0 loss by having like 1, 0, 0 or 2, 1, 1. So it's just to kind of disambiguate the different values is my guess.
Wait. I have an updated idea for it.
Okay, go ahead.
It's like a tiebreaker. You don't want it like in that one. If you didn't have it, then if you had all of the scores were exactly the same, you'd still get 0.
You'd have a loss of
Right.
0, yeah.
Okay, and if they're all the same, so without the
That's bad.
+1,
Yeah, so it's like it can't just be the. Like
so
it can't
you're actually saying the same thing.
Yeah.
Yeah,
Okay.
which is good. Okay, so this is good. This is good. What I want you to do is I want you to think intuitively about these things. So go ahead.
So my guess for the +1 is essentially that, you know, if we have the correct value, it's supposed to be negative, right? So the max is 0, so you have 0 loss if you guess correctly, right?
Right.
But the +1 is there so that, you know, even if you, okay, let's say you have like a negative 0.01, right? You barely chose the correct value, right? You're still going to have some loss, right?
So yes,
You wanna have
yes,
some-
these are good. So you're thinking intuitively. That's right. So the +1 is called the margin. So we call this is part of the support vector loss function where what you want is you don't just want a classifier. Sorry, this comes from classification land. We've had a bunch of examples of one thing, a bunch of examples of another thing. And you don't just want a classifier that gets it right. You want it to get it right with safety. So let me give you an example. So let's suppose I give you a bunch of data, a bunch of pluses over here, and a bunch of minuses over here. There's plenty of lines that will classify this properly. So for example, that line successfully classifies these and those 100% accurately. But I think you would all, like, hopefully the engineer in you is like squirming a little. Because you're saying like, the decision boundary feels uncomfortably close to the data. What I'd much rather have, what would you much rather have? Yeah, draw the line down the middle. And actually that's what this loss function helps you do. So it says if I'm too close, so if +1 wasn't there, then as long as the true class, the score is greater than all of the others,
Or equal.
then I would have 0 loss, greater than or equal to 50. But the +1 says I'm not happy until I'm at least 1 unit higher than the second highest number.
If it
And
was,
if I'm more than 1 unit higher, then my loss is 0. Otherwise, my loss is still positive. And what that's saying is saying I'm not happy until I'm correct with a margin.
if
Sorry,
it
go ahead.
was, if it
And then I'll
was
get-
like, if there wasn't a +1 and you didn't have a margins and it's just greater than or equal to, couldn't you just like spit out the same value for every? Well, I guess the scoring function doesn't like spit out the same value for everything, but like.
You're right,
You could
though.
spit out the same score for everything and just guess. Like that's the vector of like 0.1 again.
Or like if your weights were all
Yeah.
0 or
Yeah.
something. Yep.
So
That's right.
it lets you have a trivial solution.
Right, so the margin also helps get rid of the trivial
Yeah.
solution. Yeah, good. Okay, I saw it. Hand back there.
So, being that this is a computer science course, I have to ask the question, that strikes me as kind of a magic number. Is there anything about 1, or is it just any constant and that's a tunable thing that we can set up for each data set?
Any constant, tunable thing you can set up.
It's easier to scale the score
Yeah.
to the 1.
So most people don't, and the reason is, well, there's lots of reasons for that. It could be a tunable parameter that you could learn it as part of your optimization, but most people wouldn't. Most people would just fix it. And hopefully hopefully that one will have some relationship to the scores. So for example, in a minute, we're gonna talk about how you can interpret these scores as log probabilities, and then that one is gonna mean something in terms of the delta between your confidence intervals.
Okay.
Okay? All right, so great. Okay, and why is this Li, L sub I? L sub I. Good. L is for loss. Well done. Yes, so L sub I. So this is the loss on the ith example. So here's an example of calculation. So we would go through, if we wanted to calculate the loss on the first training instance, we'd go through. Why is that 2.9?
5.1 minus 3.2.
Because that's the difference between this and this, plus 1, right? Or, right? We plug that in here. And then similarly, we can go here. And so why is the loss here 0?
Because the car is at least
We
one.
got it right. That means we're happy. We don't change anything. And here, the loss, super happy. Okay? And that's because we're like way lower than the thing we would have classified it as. So this gives us a loss. So notice we've taken 3 numbers, or more generally k numbers if you have k classes, and boiled them down to 1 number per training instance. And then what we're going to do is take our overall loss function, and we'll just say that it's the average of the individuals. Okay? So this is a way for us to think hard about constructing a single number, a single loss for an entire training set that quantifies exactly how happy or unhappy we are with all the scores. And the idea is we'll plug that into some sort of optimizer and go. Okay. With me so far? Good question.
Is there some reason behind taking an average as opposed to like a mean squared error for that one, or I guess some squared errors?
Let's see. Have that. No, I don't. Okay, never mind. Yeah. So, is there any particular reason to have the? Oh, there we go. Is there any particular reason to have the mean? What do you think?
It's easy, and you've given an example.
Yeah. So there's only a little bit of a reason. It's not a super strong reason. So notice that. In some ways, using the mean versus the sum. So what's the difference between using the mean and the sum?
Normalizing?
Just that 1 over n. Does n depend on our parameters? N is, wait, what is n?
And it's the number of
Elements in our training set. So does n depend on our parameters? No, it doesn't. And so will this term ever change over the course of learning? We start with n things. We're always going to have n things. So why are we dividing by 1 over n? So the answer is just sort of engineering best practice. The answer is if we divide by n and we code up some sort of boilerplate PyTorch thing, there's going to be other constants which will depend on the scale of the loss function. And if the scale of the loss function varies with the size of our data set, then that means every time you dust off your old PyTorch code, you're going to have to retune those parameters. So things like learning rates will depend on the scale of this loss number. And so if you divide by n, that goes away. You can use the same code training on 10 examples or training on 10 million. If you didn't do that, then the losses there would be several orders of magnitude difference in the scale of the numbers you're working with.
So my question was, why are we using an average rather than like a mean squared error, or like the sum of squared errors and of those values, so 2.9 squared?
You could square them.
You don't have a ground
You
truth.
still
But
have the scale.
it doesn't, so in this particular case, it doesn't matter. None of the losses will ever be negative.
Okay.
And so,
But I mean, so if you have like the sum of squared errors, then the 10.9 will have a bigger weight than the 2.3.
oh, I'm sorry. You mean MSE on the
when you sum
on the actual numbers?
Yeah.
Oh, I see. Well, what is the ground truth number that you'd like to have pop out?
What is the what?
Sorry, you're saying for each instance define some sort of ground truth set of scores?
I think it just means the summation there, like the pluses. You could just square the 2.9 and 10.9.
These right here.
Like,
so you're saying square this.
Just like in linear regression, we use the mean squared error, the sum of squared errors.
Yep.
Rather than, that's shown to be better than just like an absolute value of the difference.
Sorry, so I just want to make sure, are you talking about squaring the 2.9?
Yeah, so like square
Yeah.
the 2.9, square the
So
0,
this
square
is-
the 10.9, and then take the
Yeah, so this is not exactly the same. So, I mean, the deep mathematical answer is the thing that you think you're doing when you're doing mean squared error is probably not what you meant, not what you intended. So mean squared error by itself is not a magical thing. It's actually derived from other principles. You can think about it, for example, as the log probability of a Gaussian likelihood in a Bayesian setting. And that's a very specific mathematical interpretation. There's a reason that we're squaring it. Here, if we squared it, it would just be for fun. So I think this is an important mathematical point. We're trying to do things principally. And so unless you have a reason to square it, I wouldn't. Because this means something very specific. And squaring it just changes that. And we're not sure what it means anymore. Okay. Anyway, Robert.
So squaring is an example of a function that doesn't change its minima, but are there other?
So that's also true because it's a monotonic. Squaring is a monotonic function, so it wouldn't change the optimum, either the maximum or the minimum, the resulting costs function. So it wouldn't. It might change the shape of it, but not where you hope to land. So I don't know. Anyway, we probably shouldn't. If you want to talk more about that, we'll talk more about that later. Okay. So a couple other questions. So I want you to talk in your group. Shoot, we have a lot of time. Okay, we're gonna. Okay.
You just add 1 to it for everything.
You'd add your margins.
Yeah.
So
Let's.
start at 1 instead of 0.
I think we're gonna have to skip these. I think this is actually your question.
Oh, yeah.
Okay. But I think this is a better question. So I want you to discuss this. So go with your groups, take just 2 seconds, and discuss what is the min and the max possible loss using this loss function. Okay. The reason I'm asking this is we're going to contrast this with another loss function in just a second.
Okay.
All right, what is it? What is the maximum? Infinity. It's not and beyond. Good. What's the minimum? 0. Yeah. So if you get everything right, you get 0, which feels unfair. So do you want to minimize or maximize this function? Minimize. You guys are great. Okay. Another question. So we're going to skip this question. So by the way, here is some example NumPy code that will implement this for us. So NumPy, how many of you know NumPy? Good, most of you. How many of you, if you're brave, can you tell me how many of you don't know NumPy? Or just like a couple of you. Okay, great. Okay, good. So here's some example NumPy code that would implement this for you. So this is a vectorized version of the support vector machine loss function. So we take our x, which is our image, take our w, dot product from that gives us our scores, calculate the margin, it's right there, and then why do we zero this out? What's going on here?
Oh, that's the if j equals y.
Oh, that's easy. It's easier than specifically. It's easier to set the margin for the right one to 0 than to specifically exclude it.
Yeah. Okay. So this is a great example of efficient hackery. So the observation is the code. This little line says sum over everything that's not the right answer. So if you were a Python newbie and a NumPy newbie, you might code up a for loop that for everything that wasn't the right answer, and you would just iterate over all the things that weren't the right answer. But actually, it's way faster if you just calculate it for everything, including the thing that was the right answer. But then you've got this extra number in there, it's not supposed to be there, and so we're just going to zero it out and then sum them all together. Okay? So it's a little bit of a hack, but results in very, very fast code. So this code is called vectorized code. So there's nothing in here, there's no for loops, but we're able to calculate this single scalar very, very quickly and efficiently. Okay? So we're going to do a lot of vectorizing in this class. So if you ever see for loops in your code, you should just think really hard about whether it's supposed to be there. And the answer is usually no, unless you're iterating over data or ethics. Okay? All right, so there's a little bug with this loss. Okay, so let's think a little bit more about this loss function. pretty good loss function. Let's suppose we find some W such that the loss is 0. You said that loss could be 0. If we get everything just right. Is it unique?
No, I don't think it's
Well, not necessarily.
Probably not.
Probably not. That's the wrong answer. I think it's either yes or no.
No, or you wouldn't be asking yes.
No, or I wouldn't be asking you.
Well, we never said it like
Yes,
unique.
'cause you knew we
Unique
think
is
that.
like unique solutions are a strong property,
This is
and I feel
fantastic.
like you should not assume that you
Yeah.
have one unless like
Okay.
it's specific.
Go ahead.
situation.
Right.
No, because we define whether something's right is not as simply as the predictions being less than the correct one. And so the correct prediction, right, could be any number as long as we're predicting things less than it, then we're right.
Yeah. Okay. Right. You're right. So clearly it's not unique. Because I asked it. Yes, that's right. Good job. I'm gonna. I have to be more foxy with you guys. So yeah. So it's not unique. So there are many different W's, all of which will give us exactly the same answer.
Oh, yeah, we have-
And so, for example, here's just like, what if we, calculate one of these loss functions with a particular set of scores? We get a 0 right here, but if we somehow made W twice as large, all the numbers change, but that still remains the same number. So this is just a little introduction to a concept called regularization. So throughout this class, there will be times when we'll see that there are entire families of parameter settings, all of which will give us the same answer. It's generally not a desirable thing, for reasons that we'll go into sort of throughout the course of the class. And so what we do is we introduce extra terms in our loss function. And these extra terms are called regularizers. And the regularizers help us pick among all the possible W's, which could give us the right answer. It's going to help us pick just one of them. So here's a little example of some regularization functions that are in common use. So typically denote R, and it's only a function of W. It doesn't depend on X. Why is that?
X is just there.
So X is data. X says something about data, but W's are weights. And we're saying, no. Lots of different possible weights could give us a 0 loss. But we want to pick one in particular. So let's imagine that we use as a regularizer standard L2 regularization. So I may at some point tell a little bit about L1 and L2, but for now, here's the function. So you give me a W matrix. I sum over all entries in the matrix, and I square all the entries and add them up. Okay, that's what this regularizer says. So let's imagine that the first part of this loss function, all this stuff,
Where does that sum? Oh, I guess it doesn't matter where the sum is. No.
let's imagine that all that stuff didn't exist. What would minimize this loss function?
Is there a parentheses around the 1 over n through max? Like, that 1 over n doesn't attach to the plus lambda, right? That's
Okay, yeah.
completely
So
outside the sum.
that's right. So usually, if you have something like this, 1 over n, it attaches to this plus, which
Yeah, I
ends
wasn't sure.
sort of there. So this is just like an extra thing that doesn't depend on I and it doesn't depend on j.
So it's add-ons.
So it's like it's outside of all of this. Yeah. Okay, so if we didn't have this front stuff, when would this function be minimized? So here's a function. It's an L. And let's assume lambda is like 1. And you give me a W. It goes through this R thing, which looks at all the entries in your W, sums them up, squares them. So when is this minimized?
When W is 0.
We're penalizing having weights at all.
That's right, we're penalizing having weights at all.
And we're especially penalizing big ones.
So, and we're especially penalizing big ones, that's right. So in this case, the regularizer is saying, all else being equal, I think that your weights should be small. You're telling me that there's an infinite number of W's, all of which would give me the same answer. Please give me back the one with all the smallest weights. Now, that's not totally true because it's a trade-off between the size of the weights and the accuracy of the classifier. And lambda
It's making it
navigates that trade-off. So if lambda is really, really big, which do you care more about? The norm of the weights or the accuracy of the classifier? Norm of the weights. And if lambda is really, really small or 0, which do you care about more? Accuracy of the classifier. Okay, good. Let's skip this. Okay, now I'd like to contrast that loss function with one more loss function. Oh, sorry, go ahead.
So you said that it's not unique without the regularizer.
Right.
Why is that bad?
Why is that So there are practical reasons. In general, we'll see that big numbers in like weight matrices typically mean that you're overfitting. So think about, for example, if we had a classifier that was like a polynomial, like a high degree polynomial, and we had coefficients on all the polynomials. Turns out you can get a polynomial to fit all sorts of stuff, but the coefficients on the polynomial have to be really, really big. If the coefficients on the polynomial are small, that means it's probably going to be flatter. It could still be wiggly, but it's going to be sort of flat. Big numbers means that it can do crazy stuff. And in general, you don't want it to do crazy stuff. So this is a way that we control the capacity of the classifier. That gives us better generalization and reduces overfitting.
So it's not just getting a unique solution, but a unique solution that works.
Right, so this is sort of like a Bayesian prior that says, we think that simpler classifiers in general are going to generalize better than more complicated classifiers. The regularizer helps us mathematically encode that. So there's also a practical issue of like, you just don't want your weights to be too big because IEEE 64-bit floating point numbers like aren't that accurate. Yeah?
Is there like a general rule of thumb on what we should set that panda to for gross data sets?
Nope. One? No, there's really not. Sorry. Yeah, so you'll find there's a lot of questions like that in deep learning, and nobody knows the answer.
They did, the guy that gave the presentation, that was his whole like PhD stuff was,
Wait, what?
does there exist an optimal lambda?
And he found out that there is a range of optimal lambdas.
Under some assumptions that won't really partake to deep learning, but just saying, that's a whole like line of research, and you can get your PhD and the Nobel Prize for
Just for that. All right, well there you go. Take lambda, Nobel Prize is yours. Go ahead.
Are there certain ranges of weights that you would say are large versus small?
How do you define large?
What would you consider a large versus small?
Yeah, I don't know, like more than 10 is probably big. Usually the numbers aren't going to end up being that large. We'll see. There are some natural scaling numbers in deep neural nets that help keep things kind of under control. So we'll see in some of the activation functions, for example, and actually in what we're about to see with multinomial logistic regression, that there are some scales to these things. Okay, very briefly, I'd like to contrast now the support vector loss machine, the SVM loss function with a slightly different one. So here's a different way we could think about constructing a loss function given scores. And that is to interpret these scores as the log probabilities of the classes. So now we're building a probabilistic classifier. You give me an image, I'm going to give you back a vector of probabilities. And I'm going to say, well, I think it's a cat with like 10% probability, but with 90% probability, I think it's a car. Okay? And so what we'll do is we will say, we'll interpret the scores as the probability that the class is a specific class, given that the input image is a specific image. Since these are log probabilities, we have to convert them to true probabilities. And to do that, we take each log probability and we exponentiate it, and then we divide by the sum of the exponentiated numbers. Okay, so just to give you, this is called, by the way, the softmax function. You're going to see this again and again and again. Just like memorize this. Okay, and then the idea is that we want to maximize the negative log likelihood of the correct class. In other words, the loss for each example image with the negative log probability of the true class given the input image. And I will just have a little picture here that I think will make everything clear. So we take the unnormalized log probabilities, we exponentiate them, and just get some crazy numbers. But then we divide by their sum, we call those probabilities, and then we say that the loss is whatever the probability was, the negative log probability of the correct class. Okay? This is a totally different way to think about constructing a loss function with kind of the same general API. Scores come in, scalar numbers come out. And we can start asking the same sorts of questions of this as we did of the SVM. So for example, what is the minimum and maximum loss of this? So go ahead and talk about it for a second. We've only got like 2 minutes left, so take 30 seconds and just noodle this.
Okay, so if everything is correct,
What do you got? What's the minimum? Zero. Why is it zero?
Because if you get it right, there's 100% probability on the right thing in log.
What does it take to get a zero?
100% probability on the right thing.
It takes what?
The frog example gets us a zero.
No, actually it
No,
doesn't.
it's, you have to.
Hold on, wait.
You're 100% confident that you have the right answer, and you're 100% confident none of the other answers are
Okay, yes. How do you get that number?
right.
So you need
All the ones, all the negative infinities.
Aha, wait, what?
Negative infinities and infinities.
Okay. Yeah, this is what I wanted. So how do you say that you're 100% confident? So this has to be, like the number on the correct class has to be something. But then what do the numbers on the incorrect class have to be? Not zero. Negative infinity. Because only each of the negative infinity gives you zero.
On the red box.
Right? So can you actually ever get 100% confident with this classifier? No. Yeah, interesting. Okay. Let's see, we've only got a minute left here. So these are two different loss functions that we've discussed, and they have different properties. Interestingly enough, throughout this class, we'll be using the softmax or variants of it, especially called cross entropy, almost exclusively in this class. And you can ask yourself some other questions, and I think we have basically no time, so I'll just let you stare at this slide for the next 20 seconds while I talk about it. The idea, though, is that I want you to start thinking intuitively about these equations. When you see something like this, I don't want you to just gloss over. I want you to ask yourself, okay, Ellie, what's the maximum? What's the minimum? How does this behave if I have some scores and I jiggle things around slightly? Actually, let's talk about this. Let's assume that those are the scores. I have these two different loss functions. What happens to the loss